Yeah, so today I'm going to share some of our recent interesting trend we see about the regolith maturation reviewed by water content to the crater ejecta deposits. So as we know, when fresh lunar rocks exposed to the surface, they receive space weathering processes dominated by impacts and radiation. It's a super complex processes, has been very well reviewed and summarized in the paper by Peters and Noble in 2016, as a cartoon shown in the slides. So here I only focus on the processes that are related to the formation and retention of water. So during the impact processes, the combination will break down the particles, the rocks into smaller particles to increase the surface volume ratio to enhance the soil implantation. And during the vaporization and agglutination processes, it can release and trap the water, both from soil wind and from impact delivered water. And the radiation process can create defects that can enhance the water formation. However, all these processes can be complicated by the impact gardening. But overall, we expect to see a trend like higher water content and a higher variation, higher diameter variation at more mature regoliths. To test this hypothesis, we're going to use the water map from the Moon mineralogy mapper and cube data because it shows a very nice downward trend as shown on the upper left plot, your right plot. We're going to use the noon data, between 10 to 14 p.m. Then you can see the variation is weaker. And also we're going to subtract the latitudinal background to see the trend clearly. We're going to examine water content at 1,672 craters with a diameter greater than 2 kilometers to make sure the deep enough materials can be exposed to the surface, receive space weathering. They were grouped into 6 age groups. Then that can be used to tell the trend with age. So here are the simple 3 steps to examine the data. So we're going to look at the water content at the crater ejecta deposits between 1.1 to 2 radii, and then we're going to exclude the steep surfaces to make sure there's no shadow. And then you say there's a similar age or younger crater disturb this crater, the pixels will be excluded to make sure we're going to use representative pixels. Now here are the results. Before we go to the trend, I want to explain a little bit about the data analysis. Say on the lower right plot, you see 2 craters, the black one and the red one. The black one is a relatively older one. Say if there's later on crater, they're kind of like an effect zone. If say there are 3 radii labeled as 3R, it's fine. They are far away from each other. There are no effects. But if the effect zone is 5 radii, you can see part of the pixels on the older crater are disturbed. So we will exclude those pixels. But if we define the effect zone as 10 radii, the whole crater will be fully disturbed. So we will definitely not use that crater. But overall, we get a multiple trends for those almost 1,700 craters at 6 age groups on the red plot. What you can see, they are in different colors, but overall what you see is for craters older than Erythrothonin, so older than around 1.1 billion years, it's almost consistent. So there's no variation compared with the background. But you do see the water at the Copernican crater ejecta, they are less hydrated. Yeah, so this is a very from different trend, different effector zone for the neighboring craters, but the trend is almost the same. And then we also examined the diurnal trend. What we see here is for the water content at older craters than 1.1 billion years old, older than Erythrothonin, they all cluster together. So the y-axis is the downward variation, the axis is the latitude. You can see it's a latitude dependent, but overall the older craters, they tend to cluster together, while the Copernican craters, ejecta, you can see the downward variation is much weaker. It's like at the mid latitude is only like 50% of those like older craters. However, this analysis is limited by the coverage of the data, so we only have like such few data points, and then we look at a different way. So we look at all the area with the repeated observations, and we use the optical maturity to represent the relatively old and a young area. The similar trend we see here. So it's like the y-axis is the downward variation, the axis is like a relative age. What you see here is like for younger age units, you see the downward variation is weaker. It's like 40, 50 ppm, the downward variation. While for the older units, you see like well, there's a steady state. You see like 80 to like 100 ppm variation down only. So there are some interpretations. We got some interpretations for why we see less hydration for like Copernican ejecta deposits. I think that could be due to less developed grain surface defects. So then that can affect the soil implantation efficiency. More importantly, we think is because there are less agglutinated formation, because there could be the major reservoir to trap the water. So on the left, you see the water profile measured from recent retained 5 samples. You can see the agglutinates profile, that's the blue line, shows much higher water content than individual like mineral grains, for example, pyroxene, plagioclase, and olivine. And we know from the red plot, we know the agglutinated formation needed time. So you can see from immature to mature, it needs some time to grow and then reach the steady state. And also there are additional processes we are still investigating, for example, the contribution from the impact delivered water. And our interpretation for the smaller downward variation of like younger crater ejecta deposits or some of Copernican, we think this can be attributed to the less developed surface defects. So it's less efficiency for those materials to receive soil wind implantation. So this is definitely testable with Apollo samples. Say we can use immature, some mature, and mature Apollo samples to radiate it and test it at a similar downward like temperature variation in lab. We can watch its variation. And there are also some indication for the time scale of this maturation processes. For sure, we need more accurate chronology for those craters and more data points. But from the data we have, we think it's like 1 billion years, like a Copernican age craters should be sufficient to mature the surface regolith. In conclusion, we observe less hydrated crater ejecta at like Copernican age. And for the older like craters like Erythronian and older, these seems like a consistent, reach steady state. And a contribution from impact delivered water is still under investigation. And we see less downward variation for Copernican crater ejecta deposits. We think the glutinate and well-developed green surface defects are key factors for maintaining the regolith hydration level. It may need like 1 billion years to have the glutinate formation to reach steady state, but it's still unclear like how long it will take for the defects development to reach steady state, or it never reach steady state. That's it. Thank you.
Thank you very much, Shuai. Maybe let's start online. Andrew, do we have any questions online?
Not immediately, no.
Okay, then we have one question in the room.
Comment, Shuai, that's really nice work, as always. Good job. A question on the interpretation for the mechanism behind it. You mentioned well-developed grain defects that keep factor to maintain the regular hydration level. That would imply you're looking at adsorbed molecular water. Is that what you're mapping, or are you mapping OH, or are you mapping a combination of the two?
Yeah, I think we map a combination of the two. And based on the M-cube data, we all know we cannot discriminate OH from H2O.
Right.
Yeah, yeah.
Because I don't think these surface grain defects would affect the formation of OH internally, right? Because that's due to implanted
Right.
protons. to
Yeah, so-
nitrogen.
Yeah, there are two parts, right? So
Yeah,
the
two
rim
parts,
part
exactly.
and the agglutinate part.
And I'm personally dubious there's any adsorbed H2O on the surface of the grains because the temperature is kind of high. So the water would probably be trapped in agglutinates like you mentioned and the honorable has shown.
I think the trapped water mostly by impacts, not the daily
exactly.
diagnosis cycle. Yeah.
Okay, thank you very much.
Hi, my name is Shaspreet. I'm a student from Georgia Tech. I have a question more on your methodology. So when you were segregating your samples with like which are mature and premature and semi-mature, how do you make that segregation? What do you use or what method do you have to determine, okay, these samples are mature, these are immature and so on?
Oh, I didn't do it, but that's back to like 1970s. People used the magnetic resonance. Andrew just presented the IS over FEO. They just empirically define like some mature, immature, some mature, and mature. So based on the IS over FEO value.
Gotcha, thank you.
Yeah.